Okay, the second half of this chapter, we're going to be looking into the chi-square test of independence. So up to this point in this chapter, we've been analyzing 2 by C contingency tables. So all I mean by that is that we had 2 rows, so 2 by C. In this case, that was 3. 1, 2, 3. So we've been using 2 by C contingency tables, and this allowed us to look into proportions, right? Because in that prior example, we were looking at the number of people who would return to this hotel out of the total number of customers, and that was a proportion. And so in that example, we had our 2 by 3 table, and we were looking at the proportion of customers that would choose the hotel again. But now we want to examine bigger tables. We want to look at R times C tables. So R is just the number of rows, where R is going to be at least 2, and C is the number of columns, where C is at least 2. So all we're doing is we're just expanding the number of rows. So if R and C are both bigger than 2, then we are no longer analyzing proportions. Instead, we're now analyzing the distribution of counts. So we don't really have proportions anymore because we have too many cells, too many rows and columns. We're now just looking at the distribution of counts. So that's the biggest difference here. So let's look at our hypotheses. So we're now just going to change our wording here, which for the null is that the 2 categorical variables are independent. The key word is independent. The rows and the columns are independent of one another. So maybe I should write that. So categorical variables, this means rows and columns. And the alternative is that the 2 categorical variables are dependent. So if the variables are in fact independent, then the distribution of counts should be the same for each group in the population. So let's quickly just go over our assumptions. So assumptions are the same as before. The first is that we need independence among our populations and samples, and all of our expected counts are at least 5. So FE bigger than or equal to 5. So those are the same as our earlier assumptions for the chi-square for difference in proportions. So let's just look at one simple example. So our heart attack and personality type independent. So type A is like the high-strung, really intense personality. Type B might be more relaxed. I'm not a social scientist, but I would imagine there are more in-depth definitions for these personality types, but let's just keep it simple for now. So we are looking at heart attack versus no heart attack. So it's suggested that people with the type A personality might be more at risk of a heart attack just because of that perhaps intense, irritable personality type. But I just want to highlight the difference between independence and dependence. So let's look at this first table on the left. Notice that all of our accounts are 20. So this is independent because regardless of personality type, the proportion of heart attacks or the counts of heart attacks are the same. So there doesn't really seem to make a difference. Whether you're type A or type B, there's the same count of people who have heart attacks and don't have heart attacks. Whereas if we look at the dependent example, if you're type A, everyone who was type A had a heart attack, whereas everyone who was type B did not have a heart attack. So we would say these are dependent because it looks like there is a strong relationship. Relationship means dependence between personality type and heart attack status. And that's kind of what we're doing. So notice that this is still 2 by 2. And so we could still analyze this as a difference in proportions, but I just wanted to stick with this simple example because we're just extending this idea to bigger and bigger tables. So in the next video, we'll review how to do a hypothesis test for this and do one more example.